Hello, I'm Václav Novotný and welcome to the tutorial of Decentralized Systems 1. In this tutorial, we will continue with the microturbines. We will show how to draw TS diagram of the cycle, QT diagram of our heat exchanger, and show something about of design performance. So, in the last tutorial, we built this model in Microsoft Excel. Now, let's draw our own TS diagram instead of the one which we have here just for illustration. So first, for the very basic TS diagram, we will get the temperature and entropy in the given nodes, where in some of them we already have it, in some of them we are missing the entropy. In order to get the entropy in all the points, all the remaining points, it's best to use the pressure and enthalpy, as these are always two independent thermodynamic variables which can be used, for example, regardless the fluid state, in case there would be wet steam and etc. So let's use the props SI function, where the output would be entropy based on pressure in here, and enthalpy here, and our working fluid is the air, and we can lock the air to use it also in other cells. So now this function can be copied also into the remaining cells, and we can draw our chart. So let's make a chart as a scatter plot, where we will put in our data. First will be the compression 1 to 2, where on the x-axis we will have the entropy, so entropy at 1 and entropy at point 2, and on the y-axis we will have the temperature. Let's use the kelvins, 1 and 2. Okay, so that's the compression. Now it looks still somewhat different than what we have here, but let's get there the other thermodynamic processes. So the second one would be compressor on the would be the recuperator heating. Recuperator heating 2 to 3. X values, entropy between 2 and 3, Y values, temperatures between 2 and 3. Next one will be combustion 3 to 4. So entropy 3 to 4, temperatures 3 to 4, and I put there the entropy wrongly, 3 to 4. Then follows expansion, between 4 and 5, so entropy 4 and 5, temperatures 4 and 5. And then we have the recuperator, where the working fluid is cooling, 5 to 6. Eventually we can add the heat exchanger for utilization of the waste heat at the very end. Now let's just give the chart some decent look. And here we have temperature in Kelvin on the y-axis, while on the x-axis we have the unit entropy in joules per kilogram and Kelvin. Okay, so we have the TS diagram in here, but now we can see that the connection of the points are just straight lines, while in real isobars or in real thermodynamic processes, the isobars are slightly curved. So now the question is, are we able to also nicely curve our own chart? And well, of course we can do that. How to do it? We will split the elements between, or we will split the process between 2 and 3 to multiple elements, get the thermodynamic thermodynamic properties for each element, and then just connect them. So let's start. Let's do it, for example, in here, and start with the change in between the points 2 and 3, and let's put in, for example, 11 elements in here, and we will have the entropy, joules per kilogram Kelvin. We will have the pressure, we can use directly pascals, temperature in Kelvin, and the starting point is the point number 2, entropy at the point 2, which is over here. Now each next point will be the difference between points 2 and 3 in entropies. So entropy at the point 3 minus entropy at point 2, while this difference we will always keep the same, divided by n minus 1 elements. It's over this because we have the starting point and then 10 changes. And this is just addition to the original starting entropy over here. And yeah, of course, we need to also log the number of elements. And here we get the entropy from the point 2 to point 3. We can check that the point 3, 4624, is 4624 in here. So now we have the entropy. What about the pressure? Again, we have the pressure at the starting point, pressure at point 2, then pressure at point 3 would be the pressure, the pressure in the next element would be pressure at point 2 plus, when we assume that the distribution of the pressure loss is linear with respect to the change in entropy. So the starting point plus now the difference in the pressure at point 3 minus pressure at point 2 divided by the number of elements and minus 1, 11 minus 1, which is here 10, and this change is always the same. So let's see, from 383 kilopascals we get to 353.096. So the entropy and the pressure are two properties that completely define the thermodynamic state, and we can use them to get the temperature. So the temperature would be again function props SI, where we want to get temperature based on entropy and pressure, with the working fluid being the air. And we can also see that the temperature goes from 454 to 859. 454 to 859. Now we can take the entropy and temperature it doesn't really much matter in the visual representation here if it's the smooth line or if it's the scatter plot with the straight lines. And we have this first change. Then for the again, let's get some nice format to that. So we will have temperature in kelvins and entropy, unit entropy in joules per kilogram and Kelvin. And this is the change to 3. So change 1 and 2 in the compressor for us will still be a straight line. We will not look in this course into some details of the compression, but we could, for example, assume the constant efficiency of the compressor, and then we would also have some curvature in this. But here let's just use the straight line as we just did it in the previous simplified TS diagram. So 1 to 2, 1 to 2. And now what's wrong in here? It did not load correct. I did not insert it correctly. And now we have the compression and the recuperator heating. Now in the same manner as we had change 2 to 3, we can make also change 3 to 4. So I will help myself in here. Just 3 to 4. where the first point would be entropy at the point 3 over here. And now we still have the same amount of elements, and we have change in the entropies 3 and 4, and this goes to the end. Similarly for the pressure, the first pressure is at the point 3, but here we did not assume any pressure drop, so we could do the same process as up there, but since the pressure is the same, so we can just copy the pressure throughout our process, and we get the temperature changes from 859 to 1123. Temperature at the end of combustion 1123. So we add this new data series 3 to 4. Again, we can get more reasonable range of the axis. And now we have the entire heating part. Now follows the expansion, so the expansion will be done in the same manner as in the simplified diagram. So now it's 4 to 5. So entropy in 4, entropy 0.5, temperature in node 4 and node 5. And now follows the cooling of the working fluid of the air in the recuperator in the similar manner as 2 to 3 or 3 to 4. Let's add 5 to 6 if I'm correct. Yes, from 5 through the recuperator to the point 6. So the entropy at the first point is entropy at 0.5. And then 10 elements and 10 elements and change between the entropy at the point 5, 0.6, will get us the 0.6, which should be 4,355. 4,355. Now let's do the same with pressure. Pressure at the point 5 over here, and then the change in the pressure per each element of our process, difference between the pressure 5 and 6. And we get into 101 kilopascals at the end. And 475.8, 475.8. So you can see it agrees. And let's add here (5 to 6), change in entropy, change in or values of entropy, values of temperature. And we could continue also similarly further on with the heat rejection in the heat exchanger for heat utilization. So now we can see that the curves are, or that the changes between the points are actually curved, as would be in the real situation, and yeah, it looks a little bit better when it's and smoother than the just connection of the nodes of the points in here. Now let's also see how the isobars look like when we the isobars that, for example, touch the point in here and here. So let's move our diagram a little bit further. And let's make isobars at, let's say, pressure would be this pressure behind the compression. So it was this 383 kilopascals, almost 384. And let's get sufficient amount of values so that the curves would be smooth. Something like this. Now the entropy, let's say the entropy range would be between these 3500 by or let's do it the other way. Let's do first temperature, and temperature going through from, let's say, 200 kelvins, temperature which will be in kelvins, pressure in pascals, and let's have the step in the temperature by 50 Kelvin. So now the range would go out up to 1500. We don't need that much, let's say just 1200. And now from the pressure and temperature we can get the entropy. Well, let's borrow just some function somewhere here. So we want entropy from the pressure, which is here correct, and temperature, which we just need to move in here. Yeah. And we get the entropies. So now let's again select data. Let's have the isobar. Pressure is 383.8 kilopascals. Values of x would be value of entropy. Value of y would be temperatures. And so that it looks better, let's get much thinner line. Okay, I did not have it selected all. Let's get over here. Let's get the line thinner with some neutral color. Okay, so here we have the isobar at this pressure at the compressor outlet, and we can see that due to the pressure losses, the pressure is really gradually a little bit decreasing below this pressure level. We can do the same also for the ambient pressure, for example, or maybe for this outlet pressure. So this would be, so basically we can copy all this and let's take the pressure at the turbine outlet, point number 5. Again, why not to have the same range in the temperatures, and it's 109, almost 110 kilopascals. Value of X, the range of entropies. Value of Y, the range of temperatures. And again we can get the line thinner with some neutral color, and so that we distinguish the pressure levels from each other. So let's have this one dotted. So we can again see that there is the ending point is little bit below, or the starting point is little bit below this isobar due to the pressure losses. Okay, so now we have the TS diagram. Let's also draw a QT, the heat temperature diagram of our heat exchanger. We can use the same principle as we had for the TS diagram. We just get the values at between the nodes element by element. Or for just rough quick estimations in single phase, as we have here, we could have used also the values gotten in here, but now I want us to do the nicely curved functions. So next thing that we do here, because we already have prepared points 2 to 3, which will be the heating part, and then points 5 to 6, the cooling part of the heat exchanger. So let's get here enthalpy. Let's say again basic units, joules per kilogram. And let's have here the transferred heat. Well, let's use kilowatts, it looks a bit better. Not such large numbers. So for the enthalpy we can use basically the same function as we have over here. Just we will change temperature to enthalpy. Same can be applied for 5 to 6. And now with the transferred heat in the heat exchanger, so the first point will be just 0, because it's the starting point of the heat exchanger, and then the transferred heat is the mass flow rate of our working fluid. In both cases, heating and cooling, we assume negligible addition of mass flow rate due to the fuel input, so just this mass flow rate of air multiplied by enthalpy difference between this specific point that we have here and always the first point, because always we are referencing the heat transfer to the beginning of the heat exchanger. And as I said that we want the heat transferred in kilowatts, so this divided by 1000. Yeah, and the mass flow rate has to be also logged. And we get the heat transfer 347, almost 348 kilowatts. So you can actually see that within the cycle there is almost 350 kilowatts of heat being recycled, while the heat input into the whole cycle is just 240 kilowatts. This is the feature of the recuperator, and this, let's say, internal recycling of the heat is the feature and the way how to get decent efficiency even at these low pressure ratios and not so high temperatures. Now the same procedure as we had here at between the points 2 and 3 will be also applied. Yeah, we already had the enthalpy, will be applied at between points 5 and 6. So again, the first point is 0, while for the next elements of the heat exchanger we have the mass flow rate, which stays the same, and difference between and mass flow rate divided by enthalpy difference between the given point and beginning of the heat exchanger. And as you can see here, the values go into the negative values. The values are negative because now the enthalpy is decreasing, but we want to see the heat in the absolute values. So basically what we could do is, in general, is always have the functions as absolute. And now we have the heat. We still have the temperatures from before. So let's use our previous graph. Just here at the x-axis we will have the transferred heat in kilowatts. And we will have just two curves. Where still the temperature is at the y-axis, while x-axis is the heat. And it disappeared because the heat goes between 0 and 350, so just get back the range. And what you can see here is that the temperatures would cross. Of course, it's not possible to happen, but this is because this is given by the side from which we are counting the transferred heat. This is what would happen if the heat exchanger would be parallel flow, but we want to have counterflow. So basically what we can just do is, in a simple way, if we have already everything calculated from this point, not from the other one. So yeah, and what we can do, just let's take the last value and lock it, minus the value. Here it will be again the same, but this one will not be locked, and we will go from 0 to 347 in the opposite order. So let's just again get the graph with the limits somewhere more comfortable. So the maximum would be 347.8, and let's go from 0. And at the y-axis, let's have the minimum at, what is it, 450. And maximum at 900 kelvins. So here we have obtained the temperature heat diagram for our recuperator. Okay, and as the last thing, we can name our data rows. So the first one is recuperator heating, and the other one is recuperator cooling. So now we have the TS diagrams and QT diagram of our heat exchanger in the system. Now, in the second part, we will have a look what happens in the off-design performance, or also in part load. Specifically, our task will be to see what happens if we decrease the fuel rate of the fuel to 2/3 of the nominal. And we will have a look which operational regime would apply and what would be the resulting efficiency. So regarding the regimes, we can have basically two of them. The first one, we could have the same airflow, meaning the same speed of the compressor, and of course also on the expander since they are on the same shaft. And the resulting of the lower fuel input would be lower burning temperature. The second regime, which comes into possibilities, which comes into consideration, is having the same burning temperature, and it could be achieved by lower airflow, that means lower speed of compressor. Now we will have a look at the first option, meaning having same airflow with lower burning temperature. So let's copy our model which we have developed previously on a new sheet or down on the existing sheet somewhere below, and let's go through modifications that we will do. Well, first of all, we don't want this model to have this iterative loop, so let's just go back to having this temperature as the temperature at the point 2 plus the pinch point. Because by this we don't have really that high error. And now let's go through the changes and different inputs that we have. So, as I said, the burning temperature will be definitely lower. The power output will not be the same. The other boundary conditions would still apply. Then the mass flow rate of the air would now become an input. So let's put it in as a value. And similarly for the fuel flow rate, it will be 2/3 of the original. And again, this would be an input. So now the heat input in the fuel can be derived from the fuel volumetric flow rate multiplied by volumetric heating value, and we have units here, kilowatts, so it would be like this. And let's also mark it green as the cell that we modified. So now, since we have the fuel input, I said that the that the burning temperature would not be this one specified, but it would be actually a result of the heat input, because we have the enthalpy at the point 3, and from 3 to 4 we already have given the mass flow rate and we have the heat input. So the enthalpy at the point 4 will be enthalpy at the point 3 plus the enthalpy difference, and the enthalpy difference is the heat input. We are calculating with basic units joules per kilogram, so multiplied by 1000 and divided by the mass flow rate. And as you can see, we get a circular reference here, and that is caused by the fact that we are using the enthalpy at the point 3, or temperature at the point 3. But this temperature is a result of the temperature at this is the temperature at the recuperator outlet, and it's function of the temperature at the recuperator inlet on the hot side at the point 5. So before we know the temperature at the point 5, we cannot know the temperature at the point 3. What we can do, or what we will have to do later, is establish an iterative calculation. But now we have specified, and we will have specified enthalpy in here. We have the pressure, so the temperature can be function of enthalpy and this pressure. Let's borrow the function for it, for example, from here. So another cell that we changed, and this one, temperature in degrees C, will be just temperature in Kelvin minus 273.15. Yeah. Now the calculation is not working, and the iterative part of the calculation will be specifying, for example, it will be specifying of the temperature at the point 3. So let's say it was almost 600 degrees C, so let's put in something less, like 500. Now the calculation is working. Let me just fix some formates. So yes, the calculation is working, but we will need to iterate this value. And how? There needs to be difference between temperature 5 and temperature 3 to be 20 degrees C. So let's put it in, for example, like this. T5 5 minus T3, T5 minus T3, and we can see that it's not plus 20 but minus 30. So that means we need to still go lower with this temperature at the point 3. So let's try 400 degrees C. Still not enough. 300, closing there, and if we put in 270, so we are roughly at the parameter that we wanted. Again, we can get the exact value by using the function of solver. So now this was our original TS diagram. In this short simplified way, we have the new one, which is already mapped for the values in here. And we can see that compared to the original, there was large recuperated heat. Also we can have a look that it was 430 kilojoules per kilogram. Now the recuperated heat is less than 100 kilojoules per kilogram. What is the result of that? Well, the most important result is probably in here, in the electrical efficiency or efficiency of the cycle, which fell from values about 30% to just about 5%. And yes, in the TS diagram we can see that the recuperated heat is much smaller, and the burning temperature, or we can see it here, that the combusting temperature, instead of 850 degrees C, the original one, is now just 460. So this operational regime probably is not really feasible, because getting just 5% efficiency. And lastly, let's see what's the net power output. Q in multiplied by electrical efficiency, and we get 7.5 kilowatts. Or if we would want the cycle power, the thermodynamic power, so it would be less than 9 kilowatts. So getting 9 kilowatts from 160 is not feasible, and let's see what can we do about it in the second option. So now we will have a look at the second regime of the part load performance, when we will have the same burning temperature and lower speed, resulting with lower airflow in order to achieve this. So for that, let's have a look at the compressor and expander characteristics, where here on the left hand side, where we have the compressor, we have curves of different speeds, which correspond to various airflow rate and pressure ratios. So we can see that, for example, between the speeds number 4 and 3, if we have the same airflow rate, so increasing the speed would mean increasing the pressure ratio, or if we would have kept the same pressure ratio at the compressor outlet, so we would get higher mass flow rate. Then on the right hand side we have the characteristics of expander, where we can see that for different rotational speeds, the gas flow rate with respect to pressure ratios is not changing that significantly. In principle, in very simplified manner, you could imagine the turbine characteristics as just a nozzle characteristics, meaning higher pressure ratio, you get a higher gas flow rate through it. But what is important is that as we decrease the speed, each speed has some maximum of efficiency, and the general trend in the efficiency going with the speed down is slightly negative. These characteristics are taken from turbochargers, but given that those are radial, both compressor and expander, similar as microturbines, so they are very similar to our case. Now let's have a look in more detail at the compressor specifically. So in this graph we have the little bit more detailed characteristics of the compressor, and we have some lines of the constant efficiency. Here we have combined compressor and expander characteristics, where let's say that the expander characteristics are the same for all the speeds, so it's represented just by single line, and the operating points are crossings of the expander characteristics with the compressor one. So for example, let's say that the nominal operating point is in here, where is also maximum compressor efficiency. Then our new operating point, let's say that it will be in here, lower rotational speed N1 with lower pressure ratio and lower mass flow rate. So in our calculation, let's assume that for this N1 the pressure ratio will decrease just to 2, the compressor efficiency will change to be 70% and expander efficiency 75%. So let's implement it in our model. So the changed parameters would be the pressure ratio, efficiency of compressor and expander, and our new input is again the flow rate of the fuel, which should be 2/3 of the original. And wiesz, a to tak wystřízno. And this fuel flow rate will be input value, so let's put it as value and input, and let's keep here V fuel of design, and let's keep here the original, and we will see in short while why to do that. And again, just to have the model not so iterative, so the temperature at the point 6 will be temperature at the point 2 plus pinch point. Okay, so the new parameters were the pressure ratio being 2. We can see that from the original TS diagram suddenly it's much more narrow, much more thin, because the pressure ratio is smaller. Then the compressor efficiency dropped from 80% to 70%, and the expander efficiency dropped from 85% to 75%. So what we can see is that the efficiency of the cycle dropped to 20%, or the net electrical efficiency below that to 17%. The cycle is much more thin. We can see the lower efficiencies of as larger change in the entropy in the TS diagram. But now there is just one last point missing, because now the model is still using the 75 kilowatts as net power output, which would result in a very high airflow rate. And our input was this mass flow rate of the fuel. And let's put here some auxiliary value as difference of the calculated flow rate minus the required fuel flow rate. And what we will do is we can iterate this value, net power output, to get the required flow rate so that we can get the required flow rate to correspond to the calculated flow rate to correspond to the required one. So let's try, for example, 35 kilowatts, still too high, 30, 29, and here by just manual iteration, or also by using the more precisely by using the solver function, we can get that the net power output will be 28 kilowatts. So we can see that it's less than half of the 75, while the heat input in the fuel is just 66%. And that's because of the lower efficiency, which is 20%. But still 20% is much better than the 5% in the first considered case of the off-design performance. So that's it in the microturbine tutorial, and see you at the next one.